Okay, guys, my name is Obina Victor, and I build backend and blockchain infrastructure right around reliability, transaction, execution, like workers, queues, RPC reliability, receipt, reconciliation, and operator facing truth, right? And today I want to talk about something many blockchain apps actually hide without realizing it, right? So as the topic actually implies, we are going to just talk about RPCs, RPC providers, and why having only one RPC provider is not a blockchain liability, right? If you want to build a blockchain product that is reliable, right? And so when you talk about reliable, we mean that in the presence of failure, this thing is actually providing the functionality or giving the user the feedback that they need, right? And so now when we talk about that RPC providers is not a blockchain liability, right? We are saying that a lot of blockchain apps are built like this. Maybe let's say the front end or the back end connect to one RPC layer, right? And so looking at this flow here, right, this our diagram here, right, you get to understand what I'm saying. So following the diagram here, right, you get to understand what I'm talking about, right, when I say that and this, like I said here, is a naive approach. It's a naive design. If you're a blockchain, if you're building a blockchain tool or you build a blockchain tool, as you always want to talk to a network, you always want to talk to a provider, right? But designing your product in this way is not actually a good design. And because everything passes through one provider, this provider, let's say that this is one provider that everything is passing through, right? Because everything is passing through this provider can actually slowly become a hidden source of truth for your system, right? And and that is very, very dangerous, right? Because the RPC provider is not the blockchain itself, right? It is just one server. The same way your normal backend system have different servers that talk to the database or talk to an external provider, right? Or you can call it maybe a gateway, right? That gives the application access to the blockchain, right? It gives the application access to the blockchain data or transaction submission. So the question here now will be, what happens when one provider is slow? When this provider here is slow, right? Or what happens when it is hidden, it is maybe behind the latest block, right? Or let's say what happens when your backend throws one weak signal and makes your financial decision from it, right? Because what can make this thing weak is because there might be a whole maybe because of the server itself, the RPC itself is weak, or because of slowness in communication, or because there is a whole lot of load, or because of rate limiters, right? These are some of the consequences or things that might cause weakness on this particular server, on this particular RPC, right? What happens? So what happens when it returns an error, when maybe let's say another provider would have returned success, right? Because let's say this provider, this server here you're using, this single server, maybe returned an error because of an issue they're having on their own end, right? Probably if you'd have run this in another server, it would have returned a success message to you, right? What will you do? These are the kind of questions you have to actually ask when you're designing a one RPC layer for your backend, right? And also, what happens when your backend throws a weak signal, right? And so that is the problem here. Like this is the challenge. This is a very huge challenge, right? And if you've worked with an infrastructure, or you've worked with a very large product, or your product is serving a whole lot of customers or users actually, you find out that this method is a very, very, very naive method, and it's difficult. It will be difficult for you to actually produce something meaningful with this, right? Okay, so having actually talked about this basic design, like I said, our focus will just be on this dashboard, right? For the rest of this, because our focus will just be on this dashboard. And so when we talk about RPC, what do we mean? RPC just means remote procedure call, right? And in simple terms, is a way for one program to ask another program or server to run an operation or to return a particular result, right? So let's say in blockchain, majorly that's where the word RPC is used majorly. So let's say in blockchain, your app does not usually talk directly to an entire network. Let's say Solana or EVM, right? Your app cannot directly, like, normally it should not directly talk to the entire network, because the network itself is huge, is massive, right? You should not directly talk to your entire network. Your app talks to a blockchain node through an RPC endpoint, right? And so this RPC endpoint is kind of a connection between your application and the blockchain network, right? That's where this RPC layer comes into play. And so when your app wants to check, maybe let's say wallet balance, it calls something like get balance, or when it wants to fetch an account data, right? It calls something like get account info, or when it wants to fetch a transaction, it calls something like get transactions, right? When it wants to broadcast a transaction, right, it calls something like send transaction, right? So the RPC provider is the bridge between your application and the blockchain network, right? And so your app asks questions like your RPC provider returns answers, right? That's just the relationship between your application, RPC layer, that's the remote procedure call, and the blockchain network, right? So the RPC provides broadcast or broadcast those information or submit the transaction. When your app submits a transaction to the RPC layer, the RPC layer actually broadcasts them to the networks, right? This actually sounds very, very simple, but it becomes risky when your whole backend depends on one RPC layer, which is what we're actually trying to demystify, right? To explain a better way to design a more reliable RPC layer, or more reliable backend system that is secure and reliable, right? And yeah, so now, this is the naive design we talked about. So let's explain. Let's actually explain this design. So let's say that a user, right? This a user, right? Maybe logged into their system, right? From the front end, right? Calls the back end, right? Um, calls the back end, right? So let's say get this transaction or send this transaction. Maybe you want to broadcast this transaction, right? Then this backend actually calls one RPC layer, right? And the RPC layer returns results, right? And the backend normally withdraws the result that the RPC layer provides, because this RPC layer is the middleman between the blockchain and the backend, right? As you can see, this process is actually common easy because it's easy for you to put one RPC layer in your environment variable, right? And your code can actually kind of read balances, send transaction, fetch blocks. You can actually check transaction status. But the problem actually is that this design works mostly on a happy path, right? It works mostly on a happy path, and this is where most design stops. This is where most let's say startups, right, stop design or start to try to patch things up instead of building stuff from a reliability point of view from the ground up, right? And so this actually, as it stands, this design, this flow actually is not the final production failure, right? What can actually go wrong from this system? Let me just give you a minute for you to think what can go wrong from this system based on what we've talked about. Remember what we've talking about here. Our major focus is on this guy here, this one RPC layer, Right? What might go wrong? What exactly do you think can go wrong in this flow? And so first, the RPC provider can be slow, right? Maybe your backend needs a response, right, in 2 seconds, right? But the provider responds after 10 seconds. Maybe the backend is actually the backend normally will be a worker, a background worker mostly, right? Is you timed it 2 seconds or milliseconds, how many seconds you want it to actually wait for a provider. But the RPC actually did more than that, right? This can be what we call timeout, right? Which is not always, or which doesn't normally mean that the blockchain failed, right? It just means that your system couldn't wait long enough for the RPC to actually finish their transaction, right? It may just mean that the provider was slow. It may just mean that the provider can be rate limited. In most cases, it is, right? It may just be that your app has a traffic, right? It may just mean that a worker is processing many requests at the same time, your back end or background workers, right? It may mean that the user or the users are checking balance at the same time. So there might be a lot of traffic, right? And the provider starts returning rate limiting errors, right? Because maybe this provider you're actually trying to reach, right? There are other applications or other dependencies, right, on the same server, right, which can actually cause a lot of rate limiting, you know, thresholds, right? And also the provider can be stored, right? This is very, very important. So when the provider may be behind the block or slot, which is most time normal when you talk about distributed system, right? When this is common in distributed system, when provider A maybe server A is actually behind the engine or the database that is providing the source, is normal. And should I go into it? Okay, so let me just talk about it in a passage. When you talk about caching and your database, caching actually handles expensive requests that happen, right? And so instead of the each time a client make a request, instead of going to the database, you can just pull from the cache, right? Normal. Now, but there are sometimes when there have been an update from the database that the cache is not actually aware of. Or Redis, normally we use Redis is not really aware of, right? This is the same thing that can happen in this system. Which the provider might be behind the latest block or slot. So your backend may ask, has this transaction landed? Right. So this might be the questions the backend can be asking. Has this transaction landed? And the provider can say something like, I cannot find it, right? I cannot find the transaction anywhere. But another provider may already have seen it, right? Let me just paint this scenario here. So let's say this is our man here, the provider we are using, right? And we have another provider here, right? And we've talked to the blockchain, and this RPC layer is our middleman between our application and the blockchain. So this is our application here, right? And this is the blockchain, right? Also, this guy didn't see our transaction. Let's just call our transaction A. Right, this guy haven't seen our transaction because he's behind the the block, right, that we actually run this transaction on. But this guy here have already seen this transaction. So now in our case, what will happen is that this man, because you're using only this guy, right, this guy will return that I've not really seen this transaction, right? And which in a normal naive design like this, you might want to return failed or the transaction didn't went through, right? Meanwhile, another server or another RPC layer have already seen this transaction, and if you return this thing to the client or you want to retry, no, you don't not knowing, or your backend not knowing that okay, this thing have actually went through, right? It will cause a whole lot of expensive mistakes where your client we have to spend more than needed for this flow. So let's say you actually retry again, right? You try this again, right? From the same server, right? It will still return the same error, right? Or the same feedback that this we aren't able to find what we are looking for, right? At the end of the day, you find out that you end up spending, let's say, on in the blockchain or itself, every transaction needs to be signed, and this signing costs some tokens, right? So let's say you've already spent like 10,000 tokens, right, trying to actually broadcast this, and this is returning a feedback of error, and your backend teams have been maybe struggling. Why is this thing not going? Why is this thing not going? Maybe they try to reach out to um the what's it called, the blockchain itself, right, and search this transaction, and they saw that okay, this transaction, 10 of this transaction have already went through, and we weren't able to get the feedback. I mean, it's I'm trying to paint the picture here, right? And that's very it's crazy, right? It's crazy. And now another issue, right? What can go wrong with this is that the provider can return an error, even though another provider would have returned success, right? So this provider might return that okay, this transaction did went through, right? While this provider can actually return that this transaction went through. And the reason why this provider might actually return error might be because of maybe temporal outage, right? It happens, is normal. Temporal outage or another provider may be healthy while this provider you're trying to use is not healthy, right? It can happen, it's normal, it's natural, it happens, right? This provider we are using might not be healthy, right? But another provider is healthy, and this provider is not healthy and is returning an error to us that this transaction wasn't successful, while another provider should have or might have returned success to us because this provider is healthy, right? And one provider may not support a method properly, like it's like that. I'm saying that there can be a whole lot of things that can go wrong for using one particular RPC layer or one provider, right? There are a whole lot of like massive, a whole lot of things that can go wrong, right? And so the issue is not just the blockchain work, right? The issue is more like, is the provider giving me or giving my backend a reliable view of the blockchain, right? Which is normally the work of the RPC layer, the remote procedure call. That's its work, for it to give you a very good feedback, right, from the blockchain, instead of you trying to reach the blockchain, the whole blockchain, right? So this gives you an API that talks directly within you and the blockchain. Do you get? So, and in blockchain system actually, the dangerous part is not only sending transaction, right? The dangerous part is that is knowing that is more like knowing what actually happened after you sent the transaction, right? Because you have actually built your logic, you have built your system, you know that okay, you've test run it and you send this out of your system, and now your system doesn't have control of whatever happens outside of this box. Remember, this is your design, right? This is where your design stopped, from the user front end and the back end, right? So your user doesn't, the transaction actually, you don't know, your backend don't know what happens outside of it, right? And so the question is not really whether the your system can send a transaction. The question is more like, did the transaction actually land where we wanted it to land? Did the transaction succeed or fail? Is the transaction still pending? Did the RPC provider not see what we sent yet, right? Did the provider time out after returning the signature, right? Or did the provider return a stored data? Did the backend make a decision from an incomplete information? Right? These are is where many systems become unsafe, right? Because what you're talking about here is more than you're trying to run whatever you want to run, right? There is a transaction happening, right? There is spending of tokens happening, and so you want to make sure that each token you spend counts, right? You don't want to be wasting tokens anyhow. I mean, and is it can make your system not to be trustworthy for users, right? At the end of the day. And so if your backend retries blindly, so because this guy here, this first RPC here we are using for the backend, return failed, right, or return any error message, right, your backend you want to retry again. It's normal. So if your backend doesn't trust one provider's storage, it may show the wrong states to users, right? Um, Maybe show the user that okay, this transaction didn't went through, right? Meanwhile, that's not the case. I'm painting this picture for you so that you see the depth of designing a very good system, the importance of it, right? The importance of designing a system that is very good and very secure, right? Designing a system that is reliable, that is reliable for users, that even in presence of failure is actually giving what you want it to give. That's the goal. That's the goal. Like if you're building a startup actually that maybe has to do with processes or data where mistakes are very very expensive, reliability, correctness should be your priority, right? Your priority should be more on reliability than whatever else you want to do at the start, right? Because you want to gain trust, you want to make sure that the first 10 users you onboard trust your system, right? They trust your system, they trust that this system is actually, when we click this button, is giving us exactly what we are looking for, right? And it's giving us a good feedback of why this thing went through, and we trust that this feedback is the final, right? Without maybe trying to look into other logs or whatever, right? And so let's still go back to this man here, right? And I believe by now you would have actually gotten the gist. So this one RPC URL, well, this RPC provider we are using here, right, might actually have timed out, or the backend receives the RPC timeout or immediately says fail. It may be lying at the end of the day. Right. I really wanted to make a video about when an API is when an API can actually return a success message and at the same time be lying. Is normal. Is things that happens when you're building a product and not having reliability at the back of your mind, right? So now let's go back to this, right? So if your backend doesn't normally trust the provider, it might provider story it actually, it might show the user this guy here, it might show this guy here, right, a very wrong information, right? And so um the question now will be, right, what's the better architecture, right? What's the better way to design this system? What's the better way to, if you want to design this system, what's the better way to design this system? And I know you'd have already gotten the gist by now, right? So a better architecture look, actually it looks more like your backend does not, normally your backend does not talk directly to one provider, right? In reverse proxy, we have what we call load balancers, right? Where you route loads to different servers, right? And so it's actually applicable to this, right? So this is your backend system, right? This is your backend system. Let's call it the back end, right? Let's just call it back end. Back end. Let's just do it back end, right? This is a backend system, and it talks to an RPC reliability layer, right? And the RPC reliability layer knows about multiple providers. Let's say provider A, provider A, provider B, provider C, provider C, provider D. So the gateway checks provider health, and so it applies timeout. It can fail over when one provider fails, right? It can rank provider based on latency and success rate. It can catch safe read methods. It can um importantly, very 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 important, right? It can compare response across providers. This actually changes the whole system, how you build a reliability, a very reliable back end system from a blockchain point of view. Now let's actually explain this diagram very well. All right, let's try to dissect this diagram well. All right, so this is actually our first provider, this is our second provider, this is our third provider, and so we have three providers. And so your backend now routes through three providers, right? And so before this actually happens, these providers, before let's say a request maybe it hits one provider or another provider A or provider B or provider C, right? The backend should have already checked the health, right? Checked, maybe can compare, like I actually mentioned before, right? Can compare provider latency or success rate, right? It can also check failovers, right? When provider A fails, I want to send to provider A. When provider A fails, it should automatically maybe go to provider B or go to provider C or go to any provider that doesn't have much requests at the moment, right? The big picture here, right? The big picture here is that you're not depending on one system. The same way you are building a distributed system where maybe you have one physical device here and you have another physical device maybe in 1,000 kilometers away from the first device, right? That's like, this is distributed in its nature, right? Where when system A failed, system B can just pick up immediately, right? When system B fails, system C can pick up immediately. So two systems can be working while system A is still under check, right? And and because this is actually in place, I mean this already actually have actually answered, I've actually clarified or given us a very big picture on how to build a very reliable remote procedure call, right? When you want to build a very reliable backend system, right? Because now let's look at this guy here, right? This guy here now has only one RPC URL, right? And this guy here has more than one RPC URL, right? And so this is talking to one backend, right? And it returns failure because of whatever it returns. Pay close attention. It returns failure, right? Or it timed out, right? And it timed out, right? Now something crossed my mind, right? That I really want to talk about now, right? When you want to handle when you want to handle the state of these products, when you want to handle the state, right? That your system or your provider returned a timeout, or your worker couldn't wait long enough and return the timeout doesn't necessarily mean that the system failed, right? I know that a lot of people design a system where they only have success and failure, right? But beyond the success and failure, we have what we call unknown or ambiguous states, right? Beyond the success and failure state, we have the ambiguous or unknown state. And unknown state is more like the state where you don't know whether the transaction that was sent out was successful. You don't really know the state. You don't know whether it's pending. You don't know whether it's successful. You don't know whether it went through. You don't know whether it didn't went through, right? That's an unknown state. Your system don't have an idea of it, because maybe the worker that was waiting for it timed out, or any error at all might happen. All right. Now, before you want to maybe retry, that's where good system design comes into play. When you want to still build a reliable system, we are still talking about the same thing, right? Amidst the having, yeah, our focus is on actually building a system where you have four failovers, right? Now, amidst that, right, we have because now being realistic here, right? having one um having this failed, right? And okay, because this failed, right? Maybe another request is coming, another request is going through this guy. Maybe let's say four requests is going through the guy. Maybe three is going through this guy. This guy only has one request, but it failed. Or your system have checked this, right? I've checked the layers and noticed that this doesn't have a good health check, or the latency and success rate is low here for this provider A, right? And so your system start routing to provider B and C, right? Now, when it's routing to provider B and C, now and a message is sent out, right? Your workers actually start waiting for these guys for the response, and the response didn't come on time, right? I just want to say this as a side note, and it's very, very important. So maybe your provider timed out while waiting, right, for the response from the provider, and because you only have a success and failure rate, your system will automatically count this as failed, right? And because it's failed, it will return failed to the user, or we want to retry the same request again, right? And you don't really know the state of that system. You don't know whether the system, the transaction, the request you made was successful. You don't know whether it failed. You don't know whether it's still pending, right? I mean, anything can really happen. But the point here is just that your system is not aware of what is happening, right? And so instead of designing your system state in a way you just only success and failure, you have to add this third guy here, which is called unknown. And so, what it actually helps you to do, right? We see, I'm still talking about designing a reliability system, and I think I've actually dealt with this. It's just basic stuff. It's nothing complex, right? Now, when you want to, I think I will still make a different video about this, but let me just talk about it, right? So now, when you want to design this state, right, what unknown means and what it help you do is that your system timed out or whatever, maybe bad communication might happen between the provider and your server, right? And maybe the provider returned failure, failed, right? While maybe the provider returned pending, right? Or because of there is an error that we call out of order, where maybe the state comes into your backend in disorderly manner, right? Now, I'm not going to that details, but what I'm trying to actually talk about here is the importance of having another state, which is an unknown. What it does for you is that when when your provider times out or your backend times out, right, you actually push that into request, or you push that because that request now you don't really know the state, right? Because you have a third state called unknown, right? You push that request to an ambiguous state, or an unknown state, or pending state, pending for review, anything you might call it. But this request, we don't know the state yet, so we cannot push it back to failure, or that the transaction failed just because whatever happened. We've not heard from the provider yet. We just know that we were waiting for it, but we couldn't wait long enough, and we timed out. Time that is one of the major reasons, right? So instead of saying that this thing failed, you push it to maybe pending state, um any unknown states, right? Ambiguous states. And what will happen here is that this is also where reconciliation comes into play, right? We call it reconciliation. What reconciliation does is actually it tries to match the provider's source of truth, the truth from the provider, with what we have currently, right? And so what is happening here is that this reconciliation will take up this guy here that is in an unknown state, right? This reconciliation will take up this guy here and check the provider to know the current state of this actual request we've made, right? Instead of returning maybe error message that this thing failed or whatever. So the reconciliation we just send, we just go and check the provider and match it with what we have, right? And this is a very good system design, right? And what it will do for you is that it will prevent you from retrying unnecessary. It will make you from, because that retry will also is expensive, it will cost you, right? It will make you from spending maybe your client's money. Just imagine, I know now there's no, I wanted to talk a bit about idiopotency, but that will be a video for another day. Right now, let's say that this guy here wasn't actually in any state, any third state, just success and failure. If it fails, your system, you want to retry again, right? Not knowing that this guy here have already, the provider have already succeeded with our transaction, just that we are not getting any feedback yet, right? But you now retry again, and you're having two transactions that have succeeded on that same intent. Is a bad design. It's a very terrible design, right? It's a very terrible design. And so this is just a very brief explanation on how to, our major focus was remote procedure call, right? Why you should pay attention to it while building um your dApps, right, or your blockchain systems, right? And having said that, actually, I built a system, right? I know this is actually very brief, but they just I think we've already gotten the gist, right? So I built a very this is my GitHub repo, right? This is my GitHub repo, right? You can come here and check this out. This is the RPC gateway. Alright, so I built one in Rust, and so I write more of Rust and Go language, right? Yeah, so you can just come to this place and just have fun, right? And you can clone this, you can fork this, you can leave a like, right? You can leave a like or star on this, or you can follow me for more. But at the end of the day, this is just yeah, this is the RPC that I built, right? And so the idea is not that I'm talking some what I've not actually worked on, which I've also worked on in production, right? Not just as a normal project. I've worked on in production, right? With some couple of teams, right? So, but now, yeah, this is just the um, yeah, this is just the flow, and this is what I've built so far. So it was purely written in Rust, right? But outside of the it being written in Rust, actually, you can actually get the gist of it on how um the flow is, the architectural design, right? Even if you don't know Rust, right, you can also understand how the design works, right? Um, Solana implementation was made on this, right? I don't know why my network is actually bad right now, but um, my network is bad. Okay. I was trying to connect back, but it's not working. But yeah, this is just the end of this brief explanation. All right, see you guys in my next video.